question then is, can we extend the concept of, let's say, input impedance to a multi-port device? With input impedance, remember, it fully characterized a one-port device across all frequency. That's all we needed to know about what was inside the blue box if we were just trying to determine the effects of that blue box outside of the circuit. Input impedance was fully characteristic, one scalar value as a function of frequency. Can we do a similar thing with multi-port devices? Well, the first thing we need to do is define a port plane for each of the ports, a location where we will define both a voltage and a current. The question then, if we have a multiport device, is how do we characterize it? We know the input impedance is a complex function of omega that completely characterizes that linear time invariant circuit inside of it. If we know that input impedance, then that's really all we need to know in order to determine what happens outside of that blue box. It gives us all of the information. Is there equivalent now if we extend that to multiport devices? It turns out there is. And that extension is something we call the impedance matrix, and it's made up of the trans-impedance parameters. So to understand what those are, first we go through for a multiport device. In this case, I show 4, although this could be any arbitrary number of ports. We define a port plane for each port, a location where we define a voltage. And notice these are complex voltages and currents. So we're talking about time harmonic signals here. These are DC currents and voltages. These are time harmonic. Complex numbers describing the magnitude and relative phase of the oscillations of voltage and current now at each of these 4 points. And of course, those values therefore will be dependent on the frequency of that oscillation, omega. Now, to be able to define accurately and repeatably the transimpedance parameters, we need to define the voltage and current at each point in a specific way. And the way we do that is, first of all, we define a voltage plus to minus, and so we define a positive voltage as a voltage potential that's higher at this location than one here. And then we define the current flowing into the plus terminal, into the multiport device, as positive. So we have an arrow going in here, 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 and here. Notice all 4 arrows are pointing into the multiport device, and they're pointing into the multiport device at the plus terminal for each of the voltages. Now, this always causes confusion for students. How do we know the current is flowing in that direction? Well, remember, we're talking about time harmonic currents here, sinusoids. Guess what? In a sinusoid, half the time the current is positive, and half the time the current is negative. Do we know the current, for example, is flowing this direction into the port 1 of the device? No, half the time the current is flowing in, and half the time the current is flowing out. It oscillates back and forth with respect to the frequency omega. Same thing for the voltage. Do we know the voltage at this node is higher than the voltage at this node? Well, half the time it is, half the time it isn't. It's a sinusoid. What we're saying here by this notation, where we have plus to minus, and where we have current flow, the arrow rather, as pointing into the device, all we're saying here is that when the voltage at this term is higher than the voltage at this terminal, then we call that a positive voltage. If the reverse is true, if the voltage at this location with respect to this is higher, then we would call that a negative voltage. Current, if the current is flowing in this direction, we call that a positive current. If the current is flowing in that direction, the opposite direction, we call it a negative current. And why is that? It's because of our notation, our arrows. That's why we always have to define the arrows. We're not saying that the current is flowing that direction. Again, half the time it is and half the time it isn't. All we're saying is the half time when it's flowing that direction, we call that positive, and in the other direction, we call that negative. And this is very important that we unambiguously define all the voltages, plus to minus, and all the currents in terms of an arrow with respect to those ports. For our transimpedance parameters, the definition of the transimpedance parameters, we must use this notation. So we have a situation where the arrows are positive, all right, when pointing into the device, and again, pointing into the device at the plus terminal of all the voltages. So make sure that you first off denote those currents and voltages in that way. This will allow us to apply KVL and KCL based on these notations, and we'll get the right answer with respect to these notations. So now the question is, what is inside this blue box? Well, the only constraint we have on that is it must be a linear time invariant circuit made up of linear time invariant elements like resistors, inductors, capacitors, transformers, and the like. Now, there may be just a few devices of that type within the blue box, or there could be dozens or hundreds or thousands or tens of thousands. It could be a very complex circuit. It doesn't matter the complexity. Regardless of the complexity, if it's linear time invariant, we can characterize it with the elements of the impedance matrix. Specifically, we're going to find all of the trans-impedance parameters that characterize it in the way similar to what an input impedance would characterize a single port device. So to determine the trans-impedance parameters, we first have to consider a case where the currents into our multiport device are all zero except for one. There's just one non-zero current flowing into our multiport device, and that's shown here. In this case, we have an example where the first current I1 is not equal to zero, it's non-zero, while the remainder of the currents, 2, 3, and 4, are equal to zero. We go through and let's say we want to find the trans-impedance parameter we'll call Z21. What is Z21? Well, it's impedance, so it's a ratio of a voltage to a current. But instead of taking the voltage ratio of, let's say, voltage V1 to current I1, we're going to take the ratio of voltage V2 to current I1. And this is why we call it a trans-impedance parameter. It's a transfer impedance, the relationship between the current at port 1 and the voltage at port 2. So we take the ratio of V2 to I1 and we get a complex number. Notice this complex number is only valid if all of the other currents are equal to zero. And this is a very important point and one which students sometimes kind of flub up on. What we're really doing here by setting the current at I1 equal to zero while all the other currents are equal to zero, is now the voltage at V2 is due to the current at I1. If we had other currents, if we had a current I1 and I3, we'd have some voltage at V2, but how much of that voltage is due to the current at I1 and how much of that voltage is due to the current at I3? What we're trying to do is determine the voltage result at, in this case, port 2, due to the current at port 1 and port 1 only. And to do that, we have to set the current at all other ports equal to zero. So this is our trans-impedance parameter Z21. Again, students flub this because they say, oh, Z21 is V2 over I1. No, only when all of the other currents are equal to zero, I2, I3, and I4, is this true. If we have a situation where I1 is non-zero, but let's say also I3 is non-zero, sure, we'll have a voltage of V2, and we can take the ratio of V2 into I1, and we get a complex number, but that complex number will not be equal to Z21. It will not be a trans-impedance parameter. It'll just be some complex number. Z21 is the relationship between the voltage at port 2 and the current at port 1 when there's only one current, and that current is at port 1. Now let's try a different trans-impedance parameter. Let's try the trans-impedance parameter, for example, of Z34. What does that mean? Well, it tries to determine the relationship between the voltage at port 3 due to the current at port 4 and port 4 only. So in this case, we have a situation where the current at port 1 and 2 and 3 are equal to zero. In our definition of Z34, we can only have a current that is non-zero at port 4. The current flows into port 4. There is a voltage that results on every port, a non-zero voltage that results, and we're interested in the voltage that results at port 3. Because we only have one non-zero current, that's the current at port 4, we can attribute this voltage at port 3 completely to the current at port 4. We can go through and take the ratio of the voltage at V3 divided by that non-zero current, and only the only one non-zero current at port 4, and that is Z34. The ratio of V3 to I4 when all other currents are equal to zero. Once again, I reiterate, if the other currents, any of the other currents are not equal to 0, we can take the ratio of V3 to I4, but it will not be numerically equal to the transimpedance parameter Z34. It really doesn't give us any information, because in that case, the voltage at V3 would be due to the current at I4, but also due to the current at some other ports as well. There's no way to separate the cause and effect, and that's what we're trying to do. By having one cause, one current, we can isolate the effect of that cause on, in this case, port 3, the voltage of port 3. So we can continue with this, and we can take any combination of ports with a non-zero current and a port where we measure the voltage, and construct any number of transimpedance parameters. And we can do this even where we look at the current, for in this case, the current at port 3, the only non-zero current at port 1, 2, and 4 are equal to 0, and compare that to the voltage at port 3. So this is sort of like an input impedance, but not exactly, because we have a multi-port device. It's the ratio to the voltage at port 3 to the current at I3 when there is only a current at I3. We call that transimpedance parameter Z33. Of course, we can do this for Z22 and 1144 example. We could do other transimpedance parameters like Z24 and Z12, any combination of 1 and 4 for our example one-port device. More generally, we'd write then any arbitrary transimpedance parameter in this form, a complex number. This is the transimpedance parameter is complex because we take the ratio of a complex voltage to a complex current when that current is the only non-zero current exciting our circuit. Again, this is very important. The voltage we measure has to be due to this one current at port N and that current only, which means that the currents at all their ports must be equal to 0. If that is not true, we can take the ratio of the voltage at port M to the current at port N, and we'll get a complex number, but it will not be equal to the transimpedance parameter Zmn. Again, this is a very common mistake that students make. Now, if we look at all this, all the different number of ports in the case of a 4-port device, again, 1, 1, and Z23, and Z41, and so forth, it's pretty easy to see that the number of transimpedance parameters that we can calculate is equal to the number of ports squared. So in our 4-port example, there would be 16 different transimpedance parameters. 2-port device, there'd be 4 transimpedance parameters. Of course, if we have a 1-port device, we get one transimpedance parameter, and that transimpedance parameter would simply be the input impedance for that 1-port device. The question we might ask ourselves is, how do we ensure that all the currents other than 1 are equal to 0? So some way we can say, you other currents, you have to be 0. We can just wag our finger and make that happen. Well, it turns out there kind of is a way where we can enforce that. We can make sure that the other currents are equal to 0. And that is to simply connect open circuits to all those other ports. So for the example where we want to find, let's say, Z24, what we need is a current at port 4 that's non-zero, but we need the current at all other ports to be equal to 0. To enforce that condition, to ensure that it is the case, we can place open circuits at all of those other ports. And so what we're doing is having a current flowing into port 4, and with respect to the other ports, we have an open circuit, and therefore these voltages are effectively open circuit voltages that we measure at those other ports. Now, I say we connect open circuits to the circuit. What do we mean by that? Well, there's two ways to connect these open circuits. There's two ways to find transimpedance parameters. One is in the lab. We have a lab bench, we have a 4-port device, and we're trying to measure the transimpedance parameters. And so this describes a real physical experiment. We go through and we put open circuits at 3 ports. We put some source at port 4, which excites some current at port 4. If we can measure that current, and likewise the voltages at the other ports, we can determine, for this example, Z14, Z24, Z34, Z44, those 4 transimpedance parameters for this case. The other way we determine transimpedance parameters is by schematic analysis. Instead of having the device in the laboratory where we excite it and then measure it, instead we might have a schematic of what's inside this 4-port microwave device. And what we want to do is replace that complex schematic with something that fully characterizes that blue box. And so we take the schematic and we do the analysis where we, again, put open circuits on that schematic and do the schematic analysis where we have a source that creates a non-zero current that we can calculate. So when we say we put open circuits on the other ports except for one, again, that may be very physical for the lab, or that may be simply a schematic modification that we make before we do the analysis of that circuit that's inside the blue box. The transimpedance then parameters can be described in this way. We can say ZMN is the voltage at port M to the current at port N when all other currents are equal to 0. Well, we're really saying when all other ports except for port N are connected to open circuits. And that's the same thing as saying that those currents are going to be equal to 0. So here again I stress the idea that the transimpedance parameters are defined when only one current, and that's the current in the denominator, is non-zero. All the other currents in the ports must be equal to 0. In other words, all the other ports must be connected to open circuits. If that is not the case, we'll still get a current at port 1 and a voltage at port 3, and we can still take the difference, or the ratio of the two, and we'll still get a complex number. But that complex number will not be equal to Z31. It'll be a different complex number. Again, what we're trying to do here is determine cause and effect, the voltage at port 3 due to the current at port 1. And the only way to do that is if there's only one current exciting the circuit. And that circuit in this case, in this parameter, is equal to port 1. So be very careful. Don't make this mistake, all right? This generally is not true. This is only true if I2, I3, and I4 are likewise equal to 0. Now here you may be wondering about the point of even doing this exercise. Why go through and analyze a circuit when we connect open circuits to all of the ports except for one? Generally speaking, if we have a useful device, we're not going to connect open circuits to it. So open circuits are basically nothing. We connect nothing to the circuit and see what happens in the analysis. Well, that doesn't seem very useful, since it's almost certainly not the case that we'll connect nothing. We'll connect every port of the device to some other useful port, and therefore every port of the device, generally speaking, will have non-zero current. So why study the case where we only have one non-zero current when almost certainly all of the currents will be non-zero? How will it help us? Will it be useful to us at all? Well, it turns out it's the transimpedance parameters. This analysis will still be very useful to us in real situations where all the ports are connected to useful devices. All the currents are non-zero. And the reason we can do this is because what's inside the blue box is a set of linear circuits. We have a linear time invariant circuit. And because of that, we can apply the concept of superposition. So let's look at a case now where we have non-zero currents at every port of our 4-port device. What we're going to find, of course, is we have voltage, likewise, at every port. Complex numbers both in terms of current and voltage. Now, can I take the voltage at V3 and divide it by the non-zero current at port 4 and determine Z34? Well, it turns out we can't, because the other currents other than 4 are non-zero. The voltage we measure at port 3 is partially due to the current at port 4, but it's also due to the current at port 1 and port 2 and port 3. Because it's linear, we can represent the voltage that we measure at port 3 as a sum of 4 terms. We'll call it V31, V32, 33, and 34. What we're saying here is that the total voltage at port 3 is due to superposition of an excitation of each of the 4 currents. V31 is the voltage due to the current at port 1. V32 is the voltage at port 3 due to the current at port 2. V33 is the component of the voltage at port 3 due to the current at port 3, and then finally V34 is the component of the voltage at port 3 due to the current at port 4. We add the four complex numbers together, and that will be our result. The measurement that we have is a superposition of the excitation by each individual currents. The question is, how do we determine then each of these individual values? So to reiterate just what I got through saying, the component of the voltage at V3 called V33 is simply the voltage at V3, the part of the voltage at V3 due to the current at port 3. V34 is the component of the voltage at port 3 due to the current at port 4. Again, the question is, how do we separate these terms? How do we determine their values? So the answer is superposition. Let's say we have a two-port device shown here with a 1 k ohm resistor and a 2 k ohm resistor. And then let's say we have two sources connected to either side of this two-port device, a 2 milliamp source and a 1 milliamp source. Now this could be DC sources, but again, we're going to stick with complex numbers. This is a current source with a magnitude of 2 and a phase of 0. Likewise, this is a sinusoidal current source of same frequency, magnitude of 1 and a phase of 0. If we go through and do the analysis, KVL, KCL, and Ohm's law, excuse me, what we'll find is the voltage at this port is 8 volts complex, and the voltage at this port is 6 volts complex. Now, let's apply superposition. Let's turn off this current source. We make it equal to 0. Well, a zero-valued current source is simply an open circuit. Remember, when we turn off a current source, it doesn't turn into a short circuit, it turns into an open circuit. And so now we have an open circuit at this port. We have one non-zero current. If we do the analysis of this, we find that this port is 6 volts and this port is 4 volts. Now let's turn off this current source and turn back on the second current source. So we have this circuit here. Again, when we turn off this current source, it makes it into an open circuit. I is equal to 0 is the description of an open circuit. If we go through and do our circuit analysis, we get 2 volts on the first port and 2 volts on the second. Now, what do we make of this? Notice if we take this solution and we add it together, we get the total solution that we began with. 2 plus 6 is equal to 8. 2 plus 4 is equal to 6. So this is an example of superposition. We can determine the voltage here, 4 volts, due to this current, the 2 milliamps current. We can determine the voltage here due to, likewise at this port, due to 1 milliamp source, and 1 milliamp source only, since this is off, it's 2 volts. And so we can say the total voltage at this port is the sum of the component due to each of the two current sources. We've identified that as a 4 volt component and a 2 volt component, which adds to 6. Likewise, the 8 volt we can now separate into two components. This 8 volts is due to 6 volts resulting from the 2 milliamp source, and also 2 volts resulting from the 1 milliamp source. We add 2 and 6 together, we get 8. Now notice how similar this is to the trans-impedance parameter. In each of these two circuits where we use superposition, we had a source at one port which is non-zero, and all the other ports, there's only one of them, but they are terminated in an open circuit and therefore have zero value current. So we go back to our more general case where we have, for example, V33, which is the voltage at port 3 due to the current at port 3. And we say that that is the voltage at port 3 that we measure when all currents other than the current at port 3 is equal to 0. Or V31, that's the voltage at port 3 due to the current at port 1. Well, that's simply the voltage at V3 we would see if all other currents except for the current at port 1 are equal to 0. Yet if we look at this, this is pretty much the same as our definition of our trans-impedance parameters. We know the voltage at port 3 when all currents except for the current at port 1 are equal to 0 is simply equal to the transimpedance parameter Z31 times current I1. Z31 times I1 is equal to the voltage at port 3 when all other currents are equal to 0 by definition. And we just found that voltage is the component of the voltage at port 3 due to the current at port 1. Same thing for V33. The component of the voltage at port 3 due to our current at port 3 can be determined simply by taking the current at port 3 and multiplying it by Z33. Again, this doesn't give us the voltage at port 3. What it gives us is the component of the voltage at port 3 due specifically to the one current I3. To determine the voltage at port 3, we would need to add up all of the components, all the four components due to the four non-zero currents. So this is what we do in our example, is to add up those four components. Again, V3, the voltage at V3 is divided into four components representing the voltage resulting from each individual current. We can determine that voltage if we know the transimpedance parameters. We know the transimpedance parameters. That's why we do this exercise in the lab where we put on open circuits, or we do the analysis of our schematics so we determine that. And then in a real circuit where we're doing something useful, where we have four non-zero currents, we can determine the voltage at port 3 by determining each component individually. And we can do that because we have knowledge of the transimpedance parameters. Now this is for voltage at port 3. We can write this more generally in this form. The voltage at port M, some arbitrary port M, we can determine by adding the terms, which is the product of the currents at each of the ports. I'll call N. N is the index in the summation here, times the transimpedance parameter Zmn, where M again is the port voltage and N is each of the individual currents at all of the other ports. Essentially, again, what we're doing here is applying superposition, and this works as long as the blue box that we're analyzing is a linear time invariant circuit. So I want to go back and one more time emphasize something that I talked about earlier, and that is the idea of the ratio of the voltage at port 3 to the current at port 1. And I said, generally speaking, that is not equal to the transimpedance parameter Z31. And we can see this now. The total voltage at port 3 is again is equal to the sum of each of the components due to each of the non-zero currents. This is our total voltage due to each of the four components, which you now can calculate if we know the transimpedance parameters. Let's take that result and divide by I1. And if we do that, we get this result here. Well, hopefully you can see that this result, V3 over I1, is not equal to Z31. It's equal to Z31 plus all of these other terms. You get a very different complex number than Z31. Now, how do we rectify this with what we know about the transimpedance parameter? We said V3 over I1 is true only if all other currents besides 1 are equal to 0. In other words, if I4 is equal to 0, well, in that case, that term goes to 0. If I3 is equal to 0, that term goes to 0. And if I2 is equal to 0, that term goes to 0. Under the condition that all the other currents are equal to 0, these terms go to 0. And in fact, for that situation, and that situation only, the ratio of V3 to I1 is equal to Z31, only when all the other currents are equal to 0. Generally speaking, we find the ratio of V3 to I1 is not then equal to Z31. It's equal to Z31 plus all this other mess. And again, I emphasize this because over and over again, I get students telling me that Z31 is equal to V3 over I1. That's almost never true. It's only true under the rare condition that all currents except I1 are equal to 0. Earlier we showed a equation which is a summation. The total voltage is equal to a summation of terms across each of the different ports. And hopefully when you saw that, you sort of thought about linear algebra. We can go back and look at that real fast here. That term right there. If you've ever had interlinear algebra, this conjures up the mathematics of matrix and vector multiplication. And in fact, we can represent then that equation, or all those equations for each port M, as a set of vector and matrix multiplications. And so this is a fundamental equation that we use in electrical engineering. This value there is what we call the matrix, the impedance matrix. And this value is our voltage vector, and this is our current vector. Now this requires some definitions here. First of all, our current vector is simply what we call a data vector. This is not a 3 vector. This is not a vector in 3-dimensional space. If we have 12 different ports on our device, we're going to have 12 different elements of this current vector. And the vector is simply a stacking of each of the complex values of the currents for each of the in ports of that device. We can do the same thing for the voltage. We take the complex voltage for each port of a device and we stack them together into an n-dimensional vector. Notice the current vector and the voltage vector have the same dimension, and that's n, the number of ports in our device. If I have a 4-port device, then this current vector has 4 elements, and likewise the voltage vector has 4 elements. The relationship between this voltage vector V and this current vector I is the matrix, the impedance matrix Z. And that impedance matrix is an n by n matrix. And so if it's a 4-port device, we have 4 by 4, having all of the trans-impedance parameters. And look closely at how this is arranged. The first column, for example, is Z11, Z21, Z31, Z41. These are all the values we got from the experiment where we put a non-zero current at port 1 and put open circuits at all other ports. This allowed us to determine the voltage at port 1 due to the current at port 1, and the voltage at port 2 due to the current at port 1, and the voltage at port 3 due to the current at port 1, and so forth. The results of that experiment lie in this first column. If we go to the second column, then we have a situation where we have Z12 and Z22 and Z32 and Z42. Again, the results of the experiment that we had in our lab or on our schematic where we made port 2 current non-zero and all other ports current equal to 0 by placing open circuits. It allows us to determine the volts at all other ports individually due to the non-zero current at port 2. The second column is the result of the experiment where our current is non-zero at port 2. So the same thing for the third column is the experiment where the current is non-zero at port 3, and the fourth column is the results of the experiment where, or the analysis where our current is non-zero at port 4. So go through and think about this carefully. This slide here is something that's used quite a bit in this class. We talk about impedance matrix and analysis of current vectors and voltage vectors. And perhaps I should have separated this into multiple pages and put blue boxes around each of these definitions, because students oftentimes will tell me, you never covered this, you never talked about this, I've never seen this before. Well, it's all in this one page, page 16 of the Multiport networks. Put a star on this and spend some time thinking about it. Again, I probably should have made this over multiple pages and big boxes. So just do that yourself. Put a big star by each of these. It takes a lot of work. Again, these are this is the fundamental matrix equation, and these are the 2 vector definitions, and this is the impedance matrix definition. And all these are important to think through, particularly in the arrangement of the impedance matrix elements. Each element of the matrix is a trans-impedance parameter. So spend some time trying to make sense of this and understand the details of the mathematics. So we said that the input impedance of a 1-port device is a complex number that fully characterizes the linear time invariant circuit within that 1-port device. It is the eigenvalue of that 1-port device. Now that value depends on frequency. Sure, if we change omega, we're going to get a different input impedance. So if I have the input impedance as a function of omega, really I have all the knowledge I need to be able to analyze a circuit with that device inserted. I can't figure out anything inside the device, but if I want to know what happens outside inside of that box, voltage, current, power. All I need to know is that input impedance. The same thing is true now for our trans-impedance parameters, our impedance matrix. Once we know the full impedance matrix of a multi-port device, then we really have all the knowledge we need to analyze a circuit with that multi-port device inserted. We can determine all external port voltages and currents and rate of energy flow, power flowing in or out of of that device. Now, that depends on frequency. So if we expand this knowledge to come up with the trans-impedance parameter across all frequencies, then we really have a complete knowledge of that multi-port device. The key thing here to keep in mind is this is implied, and it's true, that the trans-impedance parameters of our device are a function of frequency. So just because I know the trans-impedance parameters at one frequency doesn't tell me anything about the trans-impedance parameters at all frequencies. This experiment that we do where we find the trans-impedance parameters with the open circuits and such, the reality, if we want complete knowledge of that circuit, is we need to go through and determine those values across any and all frequency omega. Measuring across essentially all, or at least a wide bandwidth of omega, or doing an analysis of the schematic across all values of omega. Once we do that, we've really distilled all the information of that multi-port schematic down into a few parameters, the parameters of the trans-impedance parameters as a function of frequency. They tell us really everything we need to know to do any analysis that involves that multi-port device.